Let's explore how Python manages the visibility and execution of classes and functions within specific scopes. To start, let's look at the left side of our board. Consider this format string function. It's designed to accept a string and an optional formatter object to apply specific formatting rules. But what happens if a user doesn't provide a formatter? Well, the function simply creates its own formatter as a local class and instantiates it immediately. Because this class is defined completely inside the scope of the function, it is entirely local to it. Consequently, this class cannot be accessed or instantiated from any location outside that specific function. This logic also applies to functions. You can define a function inside another function. In Python, any statement can be executed at any time, including defining new types or behaviors. We utilize these inner classes and functions for one-off items. These are components that just don't need a global scope at the module level. They only possess logical meaning within the context of a single method. Now, let's talk about access control. Most object-oriented programming languages implement this concept as a fundamental part of abstraction. Typically, attributes and methods are categorized into three strict levels. First, private, where only the object itself can access the members. Second, protected, where access is restricted to the class and its subclasses. And third, public, where any other object or part of the program is allowed access. However, Python takes a different approach. Python does not strictly enforce these laws. The design philosophy here suggests that strictly enforcing such restrictions might eventually obstruct a programmer from achieving their goals. Instead of strict compiler enforcement, Python provides guidelines and best practices. By default, all methods and attributes on a class are publicly available. If developers want to suggest that a method should only be used internally, they can use doc strings to explain how the public-facing API should be used instead. Additionally, there are coding conventions. For instance, by prefixing an attribute with a single underscore, like variable, you send a message. While this actually doesn't stop another object from accessing the data, most Python programmers interpret this as a clear signal that the variable is internal and shouldn't be touched directly. It trusts the programmer to decide if accessing that data is truly in their best interest. But what if you want to provide a much stronger suggestion against outside access? That's where Python uses a mechanism called name mangling. This is triggered by using a double underscore prefix like attribute. While it still doesn't make the data truly private, it makes access significantly more difficult and serves as a very strong indicator of your intent. Let's look at a practical example on the right. Here we define a class named secretString. This class is designed to store a hidden string that should only be revealed if the correct passphrase is provided. Inside the init method, the constructor used to initialize new objects, we define two attributes. By using the double underscore for both self.plainString and self.passphrase, these attributes are marked for name mangling. To actually retrieve the secret, the class includes a decrypt method that takes a passphrase argument. The logic inside is a simple conditional statement. If the provided passphrase exactly matches the one stored in the object's mangled attribute, then it returns the plain string. Otherwise, it returns nothing. The key takeaway here is that Python relies on conventions and name mangling to guide developer behavior, rather than using strict compiler-enforced access controls. Next, we will jump into an interactive environment to see exactly how this secretString class behaves when we try to interact with those mangled variables. Let's explore how our secretString class behaves when we actually try to use it and see what name mangling really does in practice. First, we create our object right here. We instantiate secretString with our secret message ACME top secret and our passphrase Antwerp. Now, if we want to read that message properly, we use the method designed for it. We call the decrypt method and pass in our correct passphrase. As expected, this successfully returns the hidden string. But what happens if a user tries to peek at the data directly? Let's say they try to print the double underscore plain text variable. The interpreter stops them, raising an attribute error that says the object has no attribute by that name. This happens because Python's name mangling process changed the internal name specifically to prevent this kind of accidental direct access. You might think our data is completely secure. However, it's not truly private. We can actually bypass this protection if we know what we are doing. Look at this command. If we print the object dot underscore secret string double underscore plain string, it works. It reveals our top secret message. This trick works because of the specific rule Python uses for name mangling. When you define an attribute starting with a double underscore, Python internally translates it by prefixing it with a single underscore and the class name. Inside the class, methods access it normally because the interpreter translates it automatically. But externally, you have to use that specific mangled name to reach it. So what's the takeaway here? Name mangling is a strong recommendation, not true privacy. Most Python programmers avoid touching double underscore variables from the outside unless absolutely necessary. In fact, many prefer just using a single underscore prefix to signal, hey, this is internal, without complicating things like inheritance. Finally, let's look at how we can organize our code using packages, specifically focusing on the role of the init file. Imagine we have an e-commerce directory with a couple of modules, a database file and a products file. Inside the database module, there is a DB variable we use everywhere. Normally, reaching that variable would require a long import path like import ecommerce.database.db. To make life easier, we can add a special file. By including an underscore underscore init underscore underscore .py file in our directory, we define that directory as a proper Python package. If we put the import logic for a DB variable inside that init file, we simplify our external import dramatically. You can think of this init file as a module that represents the package itself. It's incredibly useful when you're refactoring. You might start with all your code in one big file and later split it into multiple submodules inside a package. The init file lets you maintain that simple, unified external interface while keeping your internal code neatly organized.